Could you share the screen? Yeah. Oh, share the screen. Okay.
Then we share
Share
the
the screen. This. Let's share the screen. This.
Yeah, that works.
This will work. But also just. And, let's have that.
Welcome to the solve theorem talk, I guess. Yes, as I started, this is going to be as quick as I possibly can because there's a lot to cover here, but in basically 2 parts. First part, first like 20 minutes, 5 minutes, half an hour. So I'm going to zoom through as much of Riemannian geometry, theory of Riemannian geometry as I can, which would be helpful if any of you think of doing this kind of thing, differential geometry, Riemannian geometry later on in your time here, because it's a very cool topic, a very cool subject, mathematics. And then I will show you some interesting theorems, the solve theorem and its related solve conjecture, which I will then prove as fast as I can as well, because, well, luckily the proof is very, very short, and remarkably so, and I guess you'll see it in a sec. So, yeah, so yeah, topics, general Riemannian geometry, talking about geodesics, which is a hugely important topic in physics and in geometry and everything, especially Riemannian geometry, but also physics. And then we'll talk about theorems after that. So, we're going to cover some groundwork. Manifolds, have you seen manifolds? You've seen surfaces, obviously, because you've all done analysis, right? So you've done or methods, at least methods 2 and 3 of which have done surfaces in R, in Rn, and R3. Right. But yeah, I'm going to use this board because it's so a manifold, right? Manifold is simply put a surface, but unlike what used to, it does not necessarily have to be embedded in Euclidean space in Rn, right? So I will be drawing all the surfaces. They will all be 2-dimensional surfaces in R3 because that's what I can draw. Like if I draw more, I would, but that's what I can draw. With shape, whatever. A manifold, indeed a smooth manifold, is an object, a topological object. So it's a topological space such that every point in the topological space, right, has some sort of neighborhood around it, an open set containing that point, which I can map smoothly, so diffeomorphically, actually, which is diffeomorphic means a smooth map between 2 topological spaces, to some subset of the real space. So it's a structure which locally resembles real Euclidean space. Okay? So there's obviously, you've seen this before, the sphere, right? That's obvious. Take any sort of ball around on the sphere, and you sort of the sphere, you just map it to that, right? And you've got the inverse map as well. So the sphere is obviously a smooth manifold because the map is also smooth, right? You can go higher dimensions, you've got cylinder, you've got torus. Real space itself, like 3D space, is itself a smooth manifold. Because I can map any point, the identity map, to a point in itself, right? And the dimension of the manifold is in fact just the dimension of the space it resembles locally. So smooth manifolds. Through the basics of what we have in differential geometry, and you'll find this everywhere in geometry, in topology, and algebra. The smoothness criteria isn't actually apparent always because it isn't restricted simply to Rn. If any of you are doing Lie groups, you'll find out things that the set of all n by n matrices, so the general linear group, right, so non-zero determinate n by n matrices, actually form a smooth manifold. if you do algebraic geometry, you'll find that the projective space, so i.e. the space consisting of all the lines in the space, all lines, that forms a smooth manifold, right? And of course, it becomes very confusing to talk about smoothness. Just before, let's assume that we're working in Rn, because that's the simplest place to work in, and actually everything, all the theorems hold for Rn, and they also hold for everything else. So it's just easier to think about it in that sort of way. Now, we haven't got much here. We've got a space, we've got how it looks in comparison to Rn, but we can have something more, right? It's a modular space. We can draw curves. Okay, curves. Now, we'll call them smooth curves, because if we map it to our case space, we take every point here, on that neighborhood and map it here, that curve will be smooth in here. So we'll say the curve is smooth here if the curve is smooth in its projection into the real space. Now, that's fair enough, right? We can go a bit further than that and define a vector on space. Now, you know what vectors are, lines, things, vector spaces, and all that. The way to define this isn't very extrinsic. So we're not going to, place a vector. We can't go out of the space, for example, right? In Rn, we can go out of the space. We just place a vector on a point and place it wherever we want. But on a general manifold, it doesn't really make sense. We define a vector as a tangent vector as the derivative of a curve. So actually, a tangent vector on a point, at a point on the surface, is simply the curve, in fact, the set of all curves, such that at that point there, the curve goes in the direction of the tangent vector. It forms an equivalence class, but this curve here also has that tangent vector at that point. Both these curves serve at the same tangent vector, right? And if the manifold is smooth enough, which we're assuming it is, we can do this at this point in every direction, really. We just take the curve, tangent vector, new curve, tangent vector. And the space of all these tangent vectors around that point, I'm going to make the proof here, but around that point forms a vector space. So at each point on the smooth manifold, there is a vector space formed from tangent vectors, which are, if you can think about it, parallel to the surface at that point. Now, the space can be two-dimensional, from two-dimensional, it can be n-dimensional. In fact, sometimes it even resemble normal vector spaces, especially in this case here. But every point has it, right? In fact, you can even define a new object called the tangent bundle, which is, the theory of bundles is very important throughout this entire thing, which is, rather informally, the set of all the vector spaces at every point. So at every point, you've got, take a point, take a vector from that point. The space of all these vectors is called the tangent bundle.
But you mean all the vectors, all the vector spaces?
All the vectors, and all vector spaces.
So it's like a collection of the tangent spaces.
The collection of the tangent spaces,
We
right?
call it the tangent bundle.
Tangent bundle. So it's the set, right, of the pairs a point and a vector.
Or just one vector.
Alternatively, you can, for example, we call it the tangent space. We call this tangent space at this point of the manifold M.
Yeah.
TPM, right? You can also think about this as the set of all TPM, but it's the same thing. It's a set of all vectors at all the points.
Oh, right, okay, yeah.
So we've defined a manifold, we've defined direction on the manifold in the form of vectors. Now, I think this is pretty obvious. We can now define vector fields remember vector fields in methods, something or other, in Rn, which actually is analogous to this. At every point, just pick a vector. So in this tangent bundle, just pick a bunch of points such that it's a different point at each thing. So a point here, the tangent vector on a different tangent, on a different vector space here, T, P star, P prime there, right? You pick a different vector on it. You do this every point. At this point, you put your space, pick the vector. This point, take a space, take a vector. And if you do this at every point, you get a vector field. It's pretty obvious. We'll be looking at smooth vector fields, which means just they're smooth as you go. Points close by, vector doesn't change very much. Now, this is all fine in Rn as well, but we can't really go much further than that right now, because you have your space, you have a point, tangent space, vector, a point nearby, say, another tangent space, a different vector. But these tangent spaces, TPM and P-M, they're not related at all. In Rn, they are related because they're two-dimensional. Actually, if this is a submanifold, they look like Rk and they're related somehow. But in an abstract manifold, they're not related at all. There's nothing connecting the two of them. It doesn't have to be. We can define them completely arbitrarily, abstractly, as the set of curves going through a point. And if a curve going to this point is not necessarily a curve going to that point. So there has to be no relation. Which, seeing as we in methods you have done working out the derivative of vector fields, right? So as you go along the points, how does vector field change? Right? It's easy to do in Rn because you just use a standard methods of calculus. But here you can't do it because these are two completely different objects, and you can't form a notion of bringing them close to each other. What is this vector? Vector v, vector v prime. What is vector v minus v prime? There are different vector spaces. You can't do this in two different vectors, different vector spaces. Which brings us on to the, I think, most annoying parts of Riemannian geometry. What I've spent the most on actually in the course here. The idea of connections, which is the way of generalizing the idea of derivatives on a manifold. In Rn, again, it's very obvious. Just use calculus, easy peasy. But in an abstract space, there is no inherent derivative. Now, you'll remember the idea of the directional derivative. Yeah. The derivative along a vector. On a manifold, we have this idea of a connection. So this would be an affine connection with Riemannian metric, which is the analogous definition of how to differentiate on a manifold, an abstract manifold. Now, first of all, we're going to need a little bit. It's very important, but also very easy to think about. Vector field. You've got vectors, right? On this vector field, we're going to define a bilinear form called G, right? Which is from this vector field, two vectors, bilinear form R. So R is going to be symmetric. It's bilinear. It's basically the analogous of the dot product. It can be anything you choose, right? Which makes it very annoying, but take some bilinear form on this, right? And of course, this you can extend this slightly, right? By thinking about defining it on every point differently. So there's also the same kind of actually we're defining this not on TPM at a point, say a P, we're defining this on TM and TM, the tangent bundle, right? So the set of all vectors, right? So you take two vectors of the same type. So on the same vector field, right? So at one point, right, you put your binomial form between the different vectors of the vector space, but you can define it on all the vector space, right? It's a general binomial form. Think of it as the dot product. Generalizing the dot product.
Wait. So this G, it takes value of like two vectors from the same tangent space.
Yeah, it takes
But it's applicable to any tangent space on manifold.
So yeah, it takes two vectors from the tangent space. Technically, what we like to write is GP from TPM
Right,
to
yeah.
TPM, right?
Yeah.
So you take a point, then you've got two vectors.
Yeah.
You can have your binomial form, right?
Right.
But it's actually a tensorial product, which works a tensorial binomial form, which works on every point of a manifold, right? So you've got to pick a point, you put your vectors, right?
Yeah.
Dot product. Then connections come along. I won't go into this one in detail because it's long. But a connection is, well, a derivative, right? A derivative, easy thing, right? You're doing this on the vector field, if you will. It's probably not high enough. On the vector field of, this line, you derive.
I think that's too high.
That's too high. Okay, I'll make this. Well, let's do it in all three, right? Remember, directional derivatives, you've got your surface, vector, right? And how it works, how it sort of changes down that directional, how the function changes here. And of course, you can also define a vector field on R2, right? And at every point, get a directional derivative, right? And actually, what you get up here is that you get a function from R2 to R, which you take a point, take the vector on the vector on the bottom bit, and find the directional derivative, which is just a real number. We're going to do this on here, on the manifolds. Vector field. Smooth vector field, so it's nice and easy to work with. On here. A connection is you take another vector field. Let's call this vector field here X. We're going to create another vector field. Was Y. And we ask ourselves, how does Y change along X? Now, the most annoying thing is that, sorry? Is that you can choose how it works, right? There's an arbitrary choice, it's called a connection. Number. Connection in the direction of X of Y. How does this vector field change as X changes? Right? Many ways you can think about this. It's basically analogous to this.
But just are X and Y defined as like each of the vectors at X, are those defined from one point, so one tangent space at that point, or is it just all different points, but just a smooth vector field?
So all different points, it's a vector field. So every point, one vector
Yeah.
from the tangent space around that
So
point.
each of the vectors are from different points.
Yeah.
But they are smooth, even though the
They're smoother as you go from one to the other.
Yeah.
They should change too much, right? Which is it's evident if you take into if you take your map into Rn, right? You're able to see that your vector space is around the neighborhood. So you've got one neighborhood, your vectors shouldn't change too much in Rn. We know how to do.
Yeah, but each of those points are different tangent spaces, as in.
Yeah, so you should put tangent space and you just pick one vector from the tangent space. Of course, like signs related to each other. This is why we have this object here, right? Which I will not talk about very much. It won't actually come up very much anyway, but it is the principal idea of differentiating on a manifold. Is how this, in fact, this can be any, it could be it doesn't have to be the Y here, the red one, doesn't have to be a vector field, it can be a function on the manifold, every value function on the manifold, or it can be most annoyingly a tensor value function on the manifold. you can differentiate tensors, which isn't actually that hard to do if you really apply yourself to it, but it's all manners of annoyingness and difficulty to learn. Think about this as ways of how vector fields change with correspondence to other vector fields, right? Because at every point, you've got one line, one vector, right? Every point, and you've got your other vector from the same tangent space. So we can talk about how these two are connected. Because they're the same tangent space, so you can do V minus V. And you can see how they change from that big space. I probably have to move on because we're talking about geodesics now. You may have heard of you've heard of geodesics before? Yes, maybe, okay. Geodesics, general relativity, your light curves, because the space is curved. Geodesics are in curved space, or in any space, it's not really curved, rather in abstract space, are a path such that you don't change direction. The geodesics actually first originated, well, a good example of why we need this idea is this. We've got a sphere, right? A sphere, right? I'm going to start north pole, right? I'm going to look south, anywhere south, pick a point south, right? I'm going to walk forward all the way to the equator, right? So the equator, right? So I'm walking forward, just straight forward, right? Not changing direction, forward to the equator. Then I'm doing something weird. I'm going to walk sideways along the equator. So this way I'm facing down, facing south, right? I started here facing south. Then I'm going to walk along the equator sideways, right? But curved a bit. I'm still looking south, right? Then I walk backwards for some reason, all the way up to the North Pole, and suddenly I'm looking this way. Instead of that way. This is of course, if you may have seen this before, it's a consequence of the curvature of the sphere. And in fact, if you look at the angles of this triangle, they're all 90 degrees, which is why I think falls apart in non-Euclidean space. The concept of the geodesics is such, it's the idea of going forward without changing direction. And in manifolds, it's the idea, you've got a curve, right? Manifold is curved there, you've got a curve. At each point, we've got tangent vector each curve. We know this, we've done this before. At each point, what tangent vector is this curve corresponding to? Which vector is it pointing at every point? What we want, so you've got gamma is the curve, gamma prime is the tangent vector each point, t, right? In fact, this forms a field on the curve. And we want it to not move too much. So taking this connection we just came up with, this idea of how things change compared to other things, how a field changes to another field, you've got the field gamma prime, the field of all the tangent vectors at this point for this curve here. We want it to be so that gamma prime does not change on the field of gamma prime, which is a difficult concept to come across. And I don't think I have time to explain it fully. If you want to stay after, I will try my best to explain how a thing cannot change with respect to itself.
And wasn't that like the same as the Paul product, where you have to choose in the same direction?
Well,
that's the other problem.
Yeah, the download, download that is I'm going to talk about this in Rn because it's easier to talk about it. You've got your thing, you've got your line, right? Then you've got your vectors, right? And vectors in Rn, you can just do normal calculus. Your vectors will change here. You can work out the derivative vector, right? Which is sometimes going to point outside of the surface, right? If the surface is going up, down, or going down. But we can't work with that because it's not on the surface, not on the tangent tangent plane, and in abstract terms, it doesn't work. There's nothing outside of the tangent plane or the surface. There's no like up direction. So what if I can't remember who it was, I remember in a second. The people who first started coming up with this theory just said, what we're going to do is we're going to take this normal vector, this derivative of the derivative, the second derivative really, and project it onto the tangent plane at a point. Now that's actually what this means in R3. It's called in R3, in Rn. In Rn, it's called the covariant derivative, right? It's a derivative onto the tangent plane. It's projected on the tangent plane. And color now. Got your second derivative here. Projected onto the tangent plane, right? So you've now got a new derivative, right? And if you do that on every point on the thing, what you end up with is, in fact, you end up with one field of tangent vectors and one field of covariant vectors, right? So the second derivatives projected onto the tangent plane, tangent space. Saying this is actually exactly what you can see from here, right? This, if you think of the angle between the covariant derivative and the tangent vector does not change. Which means that, in a sense, the tangent vector is walking on a straight path. The curve is going on a straight path because the way it's moving doesn't change. It's moving straight on a curvature. The curvature creates different tangent vectors, right? But the vector field is parallel. This term parallel it means quite a lot, but it basically means this: that the change in the path doesn't change, if you will. There's a lot to unpack there, really. Feel free to ask me more at the end about this, but I think we have to move on to this. A little less conceptual ideas and more just plain symbolism. We're going to introduce this function here, the exponential map on the surface. You pick a point. Here it's x. Here, point x. You pick a vector on its tangent space, txm, that is, vector v, and there's a reasonably easy proof theorem which says that if you take a point and you take a vector, there will be a geodesic, or a path, a non-changing path, which will be at point x and have this direction v. It's pretty easy to think about it. You think about it in normal space. In every space, you can have a point, and you can have a path which goes in the direction of that point, right? And it doesn't necessarily have to go arbitrarily far. It can go to only a certain extent. But we call this exponential map. It's a weird thing. It's a weird construction. It's basically the point, the vector, and you've got this path which must exist, and then you exponential map at a point x, right? You plug in a v. You plug in a direction has to go, you find the geodesic it goes to, and then you plug in 1. So exponential map of a point x with a direction vector, right, is simply this geodesic gamma at a point 1. Now, the trick that's very often used is just we add a tv, right? Which makes the vector longer or shorter by a factor of t, right? Which basically means that you go faster or slower along this geodesic, and so this becomes t, right? So at a point 1 is if you reparameterize the geodesic, you go faster or slower. go get to a point faster or slower with t, because the vector can be longer or shorter. And this will be the so you'll get gamma of t, the point gamma of t instead. Why you reduce this kind of thing is really not immediately apparent at all, but it turns out to quite a lot of times. Mainly because you just set it as rotation, but yeah, point x v. This is actually the most important thing you need to know now. That such a function works and exists for that. And now I think we have more or less enough tools to go through the next part. This isn't the theorem, by the way. This is a simple theorem, a complete non-compact manifold. That's actually a lot of terminology, so I'm saying. Of dimension 2 is everywhere non-negative with a Riemannian curvature. Is either diffeomorphic to R2 or it's flat. Okay? This is a theorem which we won't talk about later on, but which contains all terminology we need to know, right? You know that compactness topology, right? Closed and totally bounded or null, and closed and bounded. A complete, you will have heard about topology, maybe, or you will have if you do topology. Not the same thing as this. A complete basically means that any 2 points on the surface can be connected by a geodesic. Okay? Pretty standard thing. Complete manifolds are actually the study, the main study we have, because we can use geodesics of them, right? Dimension 2 is locally looks like R2. Now, curvature. Curvature in Rn is easy, right? Because you can just have normal vectors, right? In a sphere, right? You just take the normal unit vector and see how the vector changes, right? Doesn't work like that, anything, because we don't have normal vectors at all. A curvature, well, I'll just write down actually. We have a curvature tensor called R, right? R takes in 2 things, x, y, and applies it to z. The definition is connection x, there's a number x and y, z minus nabla y, nabla x, z minus nabla commutator x, y, z. I won't go into any detail. This is basically like the second derivative, right? If a connection is the first derivative, this is basically the second derivative. Take away this, right? So it's the second derivative first among x and among y, then among y, then x, then y. So y then x, then y on this z could be arbitrary. No arbitrary, but you just take this, right? And then the commutator xy, so you don't know, the commutator is just x, y minus yx. It doesn't make sense really on itself, but it's, yeah, we think about it in that way. It's basically the degree to which, it's a bit like the thing I showed you earlier on the sphere, about walking in a straight line and ending with a different thing, right? It's the degree to which the vector field changes as you go along. So you can't think about curvature in the way of a normal or like extrinsic vector, of a vector of a thing outside of the manifold. You think about it of how the tangent vectors behave, right? How badly they don't work together. Because in normal space, if I keep walking around facing one way, I always end up facing the other way. The same way, won't I? Right? If I walk around here facing this way, I walk this way with most the same points. I'm always going to face the same way because it's flat. Right? But in the sphere, it doesn't work like that. You walk one way, then you walk the same way without changing, and then you walk back, you face the other way. The curvature is a way of representing that, a way of showing how badly things break, basically.
We get like constant curvature throughout the manifold, or just their function. Was this curvature like a constant or function? Or something?
In here?
Yeah, sure.
Okay, so the curvature, it isn't really function. As you say, it uses 3 different vector fields, right? So if I get rid of the z,
So it's like an operator.
you've got two vector fields, submarine vector fields, and you get this, in a sense, differential form. But yeah, a second derivative and then a first kind of derivative, and then you take another vector field, and then you show how that vector field kind of breaks. There's a good thing we can do actually. We can to make it even easier for you, we can take let's say R2 and R2, which is flat space. We can take these vector fields, right? So the vector on the x direction, i.e. the partial derivative of the x direction, and the vector in the y direction, the partial derivative of the y direction, and this just becomes the x, dy, and so on, so on, so on, and the combinated with just dx, dy, and then dy, sorry, and dx. Well, it does actually, because R2, right, is flat. Its curvature tensor, whatever sort of you can plug a function there, whatever function you plug in there, you want to end up 0 because all these when they like commutate, they commute, so they will just cancel out. So it's all equals 0. So you've got flat space. Annoyingly enough, though, this is also flat. That's a torus, so, no, right? If you do this, right, so instead you use x, y, it turns out that this also equals 0 for a torus, and also for a cylinder. However, luckily enough, for a unit sphere, it equals 1.
Wait, I think one thing like a constant, like regardless of which
Yeah, so anything you take, any vector
you will
field,
always be
you'll find that the degree of which the vector field breaks is 1. That's only for a unit sphere. It actually is if the radius is just, yeah. And if it's constantly negative, you have hyperbolic space, right? So things which further something infinite. So this theorem here, which we almost non-complete, non-compact manifold dimension 2 with everywhere non-negative curvature, right? So the curvature doesn't have to be the same everywhere; it can change. Everywhere non-negative is either diffeomorphic to R2, so smoothly maps to R2, or is flat.
flat, I think. Like curvature theory.
Yeah, I mean it's kind of works by definition, but it's a very simple theorem. It just helps us because next we have this, which is the generalization. Let M be a complete non-compact manifold with non-negative sectional curvature. Then M contains a compact, totally geodesic and totally convex submanifold S whose normal bundle is diffeomorphic to M. Not to unpack there, but we've done this. Complete we know, non-compact we know. Sectional curvature is related heavily to normal curvature. It's a bit simpler though. You put your tangent space, you take a sub-vector space, two-dimensional sub-vector space, vector subspace, sorry, right? Two basis vectors, and then your, so let's say two vectors there, U and V, your tangent, your sectional curvature is, I'll draw the definition down, is the, so G, which was our dot product, our Riemannian metric, R, U, V, V, U, over the area of a parallelogram, which abounds. It's a simpler concept. I'm not going to describe it here. It kind of works like normal curvature. Yeah, and M contains a compact, normally compact, totally geodesic, meaning that every 2 points, empty points, right, on the thing have a geodesic contained entirely in the submanifold.
Now, what's this relationship with complete?
Sorry?
Like totally geodesic, they imply complete or complete imply totally geodesic?
No, because it is complete that the manifold using any 2 points have a thing, right? But if it's totally geodesic, if you take the submanifold, right, you could have 2 points,
yeah.
But you could also have maybe the only geodesic goes outside that manifold to connect the 2 points.
So for example, let's say a torus, like the whole, the 2 points there.
Yeah, so for example, actually we don't work the torus because the in the torus in any embedded thing in Rn, anything which can be any compact complete thing should be totally geodesic. But it's basically you've got your imaginary surface, right? And you've got normally if you have 2 points, you should be able to connect them here,
yeah.
right? But imagine the thing is so annoyingly warped that there's like a thing in the middle which doesn't work. And the only geodesic that connects it is this, which goes outside this manifold.
Then it's no longer totally geodesic.
Then it's not geodesic, right? And totally convex. Let's not once again. Okay, I've got a second. Right? As soon as I remember, but it's a similar kind of thing about it being entirely contained within the manifold. That's the sort of thing, right? It's a generalization of this. And it's a pretty interesting theorem because the corollary, right, is that the normal bundle, which is the tangent bundle, right, of this thing. So we just take the vector space on submanifold S. But the normal bundle is all the vectors in this normal bundle, which are orthogonal. So orthogonal with this geometric, dot product metric, whatever, all vectors which are orthogonal to all other vectors in M. It's annoying to think about it this way. Manifold M, submanifold S, the normal bundle is just these normal vectors. Now we're saying that the combination of all these normal vectors is diffeomorphic to M, which is a pretty strange thing because of this next part, this whole conjecture. Pretty much the same thing. Complete connected, we assume it's connected anyway, non-compact, sectional curvature, non-negative, and they disappoint where the sectional curvature is strictly positive. Then the soul of M, this totally convex, totally geodesic thing, is only a point. And furthermore, M is diffeomorphic to Rn.
Wait, by so you mean the submanifold?
Yeah, the submanifold. The submanifold which works. So the Soul theorem has proves us that there exists something, right? But this Soul conjecture shows that if you have the additional condition that a point where the sectional curvature is strictly positive, so it's totally flat, then the Soul is a point, and because a point, the normal bundle is just it's the entirety of the tangent space, really. Because everything is orthogonal because it's only a point, it becomes 0. And because this tangent space is Rn, this is an n-dimensional manifold. And then this tangent space is not this bundle, because at only one point, the bundle becomes just a space. There's only vectors. This space becomes the entire manifold. Which means that if you have these conditions, you can tell that the manifold is basically just Rn.
Wait, what do you really mean by diffeomorphic? Like
smoothly.
Yeah, so like
a smooth bijection.
What does it imply? So like sub isomorphic.
Well, it implies that if it needs a structure, a sphere, we know, is two-dimensional, but it is not diffeomorphic to the plane.
Yeah.
Right?
Yeah.
You can it's a sphere minus a point.
Just zero graphic projection.
Yeah, exactly. A sphere minus a point is right? Yeah. But a sphere. The sphere has has yeah, a sphere doesn't have all everywhere sectional curvature. Yes, so
You know, like my question really is like we going to say that M is differential Rn. Like, what does it really imply? Like, what can we do about it? If
what can we do with it?
Yeah, like if you know M is differential
A question from an applied mathematician. No.
No, not in the sense of do something, but like in theory form. Like, what's so yeah, like what's so important about it? Like, what else can we learn from this?
Well, in topology, if something is homeomorphic, it's the same thing. I mean, most of the time it's obvious that this is something. For example, with the projective space,
Okay.
we see that the projective space is actually defaulted to R to 2n. We can't. I think we can use that, but the sectional curvature on projective space is very annoying to work with because of the nature of what's the tangent space of the lines.
So let's work with SL2 art.
Sorry?
SL2 or special linear.
Special linear group. I don't think the special linear group has everywhere non-negative sectional curvature.
How do you calculate it? How do you calculate it?
You take your connection.
How would you define it on SL2Z or SL2R? You do like
How do you
can you prove that it's not negative?
non-negative? Well, I definitely try.
It's all abstract, but like example.
Okay, fine.
Maybe you can just go on with your thought, then we can come back to this one.
I'll give you an example at the end.
Yeah.
Since things were pretty much near the end of this, I'm just going to zoom through the proof. The proof given by this guy. Yes, that's right. The man, the legend himself. He proved it shortly after he graduated PhD. It was an open problem. The solved theorem was proved earlier by Cheeger and Gromoll. It was open for 5-6 years, and he came along and proved it. Proved it in 4 pages. Which, for a proof in, what is it? 79, kind of, it's quite a short proof. Math papers nowadays are very, very long. It seems we only have like 10 minutes left. Here's the theorem he gives. So the solved conjecture is actually a corollary of this theorem. A pretty easy theorem to prove, actually. M complete non-sectional curvature, S be the sol being the totally convex, totally geodesic submanifold we have, the sol. And P from M to S being a distance non-increasing retraction. A retraction is just a map which takes this thing takes M into S, right? Retracts it such that the restriction of P to S is just identity. And if you think about it, manifold, so everything into that. And distance not increasing, the distance between 2 points is just the length of the shortest geodesic. It's complete, there must be a geodesic. Take the shortest one, take the infimum, actually it's minimum because there are finitely many, but take the minimum of geodesic, that's the distance, right? So the distance between 2 points is not increasing. Then we have 2 parts for all points to the sol, and for all news in the unit normal bundle. So normal vectors, the sol. We have that. Go bracket there. If you take a point on the sol, right? Exponential map, you take the geodesic outwards to a point, and then you retract it back through this retraction called the retraction, right? It will be itself, right? That's weirdly enough because you can take any normal thing. 1 point, and then geodesic, very geodesic you have in the soul, vector field parallel to it, so that the connection on the field it doesn't change, it's parallel, keeps going along. Then the horizontal curves, which I'll show here, you basically take your normal vectors and you make new geodesics out of it, new geodesics. They fill a strip up, so just geodesic, strip of geodesics. They're actually flat, i.e. the sectional curvature is 0. Yeah, so you fill a flat strip, sectional curvature ends up being 0. And then if you take this geodesic between 2 points, geodesic, it's minimizing, i.e. the shortest geodesic between 2 points. Then any of the other geodesics are also the shortest one. Seems evident, proof isn't that long either. Now there is a proof, and I probably do not have time to
that's just.
go through it. I'll just say the last thing, which actually the corollary, is this. So from the theorem we had earlier, the corollary is this. We find that the exponential map we used to find earlier, this exponential map, right, which works only in normal vectors, is surjective, which means that we can find a geodesic onto this point here, right, which has strictly non-negative curvature, right? Now, and this is a quick contradiction, if we assume that the dimension of the soul is greater than 1, then this point will exist inside this flat strip, right? Because we've got the geodesic, we just create the flat strip around it, right? The point will exist in it, which means that its curvature, its sectional curvature, will be 0 because it's flat. However, contradiction, of course, because we assume the point had non-negative sectional curvature earlier. Therefore, the dimension of the soul is 0, which means it's a point. And the corollary here just simply follows through the soul theorem. Go back. That the normal bundle, i.e. the section of all points, is the more. This is all I have time for, I think.
I think we have a question for now. Not time for that, but
if you have any questions,
catch me
outside.
outside. Thank you, Matt, for this amazing talk, and I'll pause the question for now. And I'll do that.
Joueur dans le